Hello everyone. The textbook we used is the author is Stewart. Stewart. We will teach from section 1.5 because before 1.5 they are pre-calculus. You should have learned before university. So the section 1.5 is the limit of a function. 1.5. The limit of a function. Okay, before the function, yes, here in the first semester we will consider functions from a real number line to real number line. If a number x is given, then there is one and only one number corresponding to x by this this rule or this letter f we call f of x, or the value of the function f at the number x, f at x or f of x. And the graph of the function is the set of all ordered pairs whose first coordinate and the second coordinate has this relation, or the collection of all points satisfies this equation. Such an object or a curve is called the graph of the function. The graph of the function. So here, sometimes we call x independent variable. F function. F of x, the value of the function at the number x value. So usually x is a number, f of x is a number, f is an object or set object. This object is a rule combined two numbers. Yes, ordered pairs. When x is given, one and only one number corresponds to that number. Okay. Then this is the graph of the function f. In terms of set, this is the set of all point x, y in the Euclidean plane such that y and x has this relation. The graph of f. Okay. Before, if this relation or this function is a linear function, then the graph may be a straight line, or a quadratic function whose graph is a parabola. What if the graph of a function is not a complete curve? If the graph with some gap, for example, looks like this. There is a gap here. A circle, empty circle. Suppose this is the number A and this is a number L. Pretty like if this is none of C. here without a gap. Here, there is a gap with a gap. In this case, we know L equals F at C. But here, we almost want to say F of C equals L. But unfortunately, F is not defined at the number C. Fortunately, F is defined in some neighborhood of C. Even not defined at C, but defined nearby C. Nearby C. So this determines the behavior of F around C. As you can see, if this neighborhood is we choose some smaller neighborhood of the point C, then we get a smaller neighborhood of this point and smaller neighborhood of L. We give this phenomenon a notation. We can't use this one because F is undefined at C. Then we use this notation. The limit of the function f of x as x approaches C equals L. Equals L. Okay. This is the notion of limits. Limits. Of course, if f is defined at C, we can talk about limit in this case. Okay, ignore C. F is still defined as some neighborhood of C and C. This defined on some neighborhood of C except C. When we talk about, we are talking about limit, we never consider the number C, the position C. So ignore this one. We just consider values nearby C. Oh, nearby C. Nearby L. Good. So this case we still have x approaches C, the limit of f of x equals L. Same. Okay. Now some different occurs. Here f is defined at C. Here f is undefined at C. In the future, we will say if this L is exactly the value of f at C, then we will say f is continuous at the number C. Continuous says the graph is without gap, not cut. This is f is not continuous at C because seems cut by some scissors. Cut with a gap. Talking about limit, we never concern this position C, but a neighborhood of C. Therefore, if a function f whose graph is almost the same as this, almost the same as this one. Again, this is C. This is L. But we have a jump here. C, f of C. I mean, this is f of C. In this case, this statement, the limit of f of x as x approaches c is L, is still valid. Because if on some neighborhood of the number c, the values of the function f is in some neighborhood of the number L, C we never consider. We don't care when we talk about limit. So here, this relation is still valid. It's true. Okay, so continuous. This continuous at C. This is also discontinuous at C. These two graphs, or this three. I use the same FO. Maybe I had better use G of x, H of x, maybe. So talking about limit, we don't care the exact value of the function f at c. Maybe defined, maybe undefined. Defined like these two cases. Undefined like this one. There's a gap. They are all the same. All the same. Okay? This is limit. In fact, this concept of limit is two-sided limit. If a function are only defined on one side, for example, we consider, okay. Y equal the square root of x. In this case, this function, a square root function, only defined for x is non-negative. Only for x is non-negative. So when we're talking about this one, the limit of the square root of x as x approaches 0. This seems not so so proper, so suitable for talking about this issue. Because only the right-hand side of the origin is defined, so we had better put a plus here. Means we consider some neighborhood of 0, but on the right-hand side, on the right part of the number 0. So we have this so-called one-sided limits. Okay? Mm-hmm. In this case, we have considered a neighborhood of the origin 0, then the behavior of the function looks like this. If we call this is the diameter, not diameter, radius. If the radius is smaller and smaller, then this portion will smaller and smaller, and this one always also smaller and smaller. This case, we use this notation to indicate this phenomenon. Okay, this phenomenon. So this is one-sided limit. One-sided limits. One-sided limits also can apply to a function of, in this case, for example, we have a linear function here, a quadratic here. This is C. Or there's a gap here. Suppose this is M, this position is L. The function f combine two different formulas. One is linear on the left of the number c, another is quadratic, I mean a polynomial of degree 2. In this case, we can write the limit of the function as x approaches c from the right is what? L. And from the left, is M. L and M are not necessarily the same. Not necessarily the same. Maybe different. Maybe different. So now we have concepts of two-sided limits. We also have concept of one-sided limits. Okay. Can we conclude these two concepts? Some statement is true. Yes, we call this as a theorem. Theorem is a statement can be shown or can be proved is a true statement, a true sentence. So the theorem says a function f, the limit of a function f